Welcome to the class of intelligent product design, and today we will talk about a very important factor which we must consider while considering the material for a particular design, and this factor we will call it as the shape factor. Okay. So, shape is a very important element in any, be it natural, be it artificial, in any form of a structure or a system, right. Like consider the type of deers, the shape of the horn plays some very important role in terms of clearing obstacles. You see, shape plays a very important role in any form of structure. Consider, for example, the simple watermelon, and you can see that in Japan people put different types of container in the growth phase itself of the watermelon, the shape of which must have been designed by nature from the seed dispersal point of view, from other temptations, but from the human point of view, because of the organic material that it has, it actually provides sort of a opportunity to create different shapes of watermelons, and the shape matters. Now, when we talk about shape, say for example, we think of any structural system which is maybe subjected to bending load or torsion load or compressive load. Okay. So, we are thinking of the shape right now in the mechanical context. Later on I will come from the aesthetics point of view, but in the mechanical context, whenever we think of the shape, that means the shape would be important if, let us say, a certain structural member, again I will take our simple example of a cantilever beam, is subjected to bending. That is one possibility. Another possibility is that, again, another type of a cantilever section which is subjected to not out of plane, but in plane torsion. Okay. So, that this cross section would get distorted, the in plane torsion. So, that is the torsional part. Shape becomes important here, we will very soon see. And also a system, maybe it is subjected to compressive load. So, that is the compression. Shape becomes important here also. Actually, you will see very soon that the shape, wherever the area moment of inertia plays an important role, the shape automatically becomes important. Now, when I talk about shape, what I mean is the cross section, and there are various possibilities of a cross section, like I can have an eye section of each one of them, I can have a hollow box section which would look something like this, a hollow box, or a sandwich panel. That means there will be three different members together, and the panel inside is actually sandwiched. This is the part which is sandwiched inside two face plates. Then there can be ribbed panels which will look something like this, that basically it will be a panel, but it will have in between such ribs. Okay. Then there can be tubes. Tubes are another form of a hollow box section. Both of them are good in terms of torsional point of view. So, this is like a tube. So, all these, when I talk about, they are having different types of cross sections, and that is what we have to check, that how in the material selection phase itself we can take that into consideration. And when we say it is efficient, we say that efficient because it is a certain shape if it uses least material for given stiffness or strength. Now, you must note that shapes to which a material can be formed are limited many a times by the material itself. There is something called ductility or formability of a material. So, not all the material can be given any type of a form, there is a kind of a restriction in it. Now, whenever we will compare the shape efficiency, we have to consider a baseline system, okay, a baseline cross section. Now, one way is that you compare the cross section with a solid cylindrical cross section. So, this is a solid cylinder, let us call it as I cylinder, okay, and this is what? This is I tube. So, if I try to see that I cylinder has a different type of area moment of inertia in comparison to the I tube, and in fact, the ratio between the two will be something like 1/4 R by T I cylinder for the same area. Now, the inertia is different, that is one point we have to keep in mind as we change this cross sectional shape. By basically changing the cross sectional, we mean that how the material is distributed with respect to the neutral axis. And then what we can do is that we can compare the stiffness. For example, if I consider this as the tie beam, then we are basically giving a tensile force to the system. Now, against the tensile force, its stiffness is EA by L, and since there is no I there, which means for a tie beam against tension, cross section does not matter, cross section does not matter, because there is no moment of inertia in the expression. So, the cross section does not matter in this case. Okay. So, that is the point that we have to keep in our mind, that cross section does not matter. On the other hand, if I think of a beam which is going to carry a moment, that is the bending moment we said, then what is the stiffness of it? The stiffness of a beam is some constant which depends on the boundary condition times E I over L cube. So, here the area moment of inertia has appeared, and as the area moment of inertia has appeared, here the shape matters. That means, how the material is distributed with respect to the neutral axis will actually change the area moment of inertia, and that will actually change the stiffness of the system. And hence, for this type of a system, if I compare this stiffness with respect to a base stiffness, like let us say for a same area, but either solid circular or a solid square cross section, then we will be able to actually add this new factor which is called the shape factor. Now, you look at the tension member tie, as I told you that area A matters here, but not the shape against the tensile load. This is subjected to tensile load. But if I consider bending of the beam, then both area and shape, particularly Ixx, Iyy, both the bending moments would matter. If I consider torsion, okay, so there is something which is twisting the system. So, against the torsion, area and the shape in terms of the polar moment of inertia. So, this is actually polar moment of inertia. So, this would definitely matter. If I consider compression in a column, here also I minimum between the Ixx and Iyy, the I minimum would actually matter. So, for certain structural elements like for beam, bending, torsional shafts and compressive columns, the shape factor would matter. So, then we accordingly need to have 4 different types of shape factors. Okay. Phi BE, which is elastic bending of beam related shape factor, phi TE, which is elastic twisting of shafts shape factor, phi BF, it is failure of beam in bending shape factor. So, this is against failure, sigma phi TF, which is failure of shaft in torsion. Now, why the shape factor for the strength is different than the shape factor for the deformation or stiffness? Well, that is because you might have noticed in the earlier slide, I will just go, that there is a section modulus Z, which was I over y max. Now, this Z also is going to vary corresponding to the strength, because that is what plays a very important role, because as you know from the theory of bending, that we can basically write these in terms of, say, sigma maximum stress, sigma max over a cross section. So, sigma over, so it is m by I am writing this in this side, m by I equals to sigma max by y max. So, that means sigma max maximum stress is actually m y max divided by I, okay? And that means this is m divided by z max, and this section modulus, that means is different from simple I, and that is why you need a different factor for the strength. So, the failure point of view, you need two different shape factors. Now, all these things I need to basically normalize. Either we normalize corresponding to the area of a solid cylinder, or we normalize corresponding to, it just a matter of convention, corresponding to a square. Okay. So, either of it. Okay. Now, how do I obtain this shape factor? Well, exactly as I told you, that consider these cases where you have different types of cross sections, where however the area is constant in all of them. This is also A, this is A, this is A. Suppose the area you keep it constant, then the shape factor is defined as the stiffness of this element, like let us say this element over S0. So, this is like stiffness of the reference element. So, this stiffness we know however is proportional to EI. So, it is EI over EI0, and that I, you know that I0 is basically like pi r to the power 4 by 4 can be written as a square by 4 pi. So, this with respect to the circular cross section, if I consider this to be a 0, then phi b e will be 4 pi I over a 0 square. Okay. So, that is a 0 square. So, that is the the shape factor against bending. Now, one important thing you have to keep in your mind, that shape factor is actually dimensionless. Okay. It only characterizes the shape. Okay, because if you look at the earlier expressions, okay, you can very clearly see that I also has a unit of meter to the power 4 and area square has a unit of meter to the power 4. So, they cancel. So, it becomes dimensionless. So, basically shape factor does not depend on the actual area. It only signifies how the material is distributed, distribution factor. So, for all the I sections irrespective of their size, the shape factor for example is 10. For all the circular tubes irrespective of their size, shape factor is 10. Okay. So, this is one important point. Secondly, as we actually keep the shape constant, we get roughly this shape factor 10 means with respect to the cylinder it is 10 times stiffer. Okay. So, we get more and more stiff system. Now, sometimes of course, we may need low stiffness like say springs or say suspensions. So, in such a case we would not go for the value of phi e which is greater than 1, but we will go for, so this is for stiffer section, and but we can go for phi which is less than 1. So, this is for softer sections. So, both of them are important depending on the applications. Another important point is that shapes that resist bending well may not be good in terms of the torsional resistance. For example, if this shape resists bending well, the I shape, so this is good in bending, this is good in bending, but from the torsional point of view, so this is good, these tube shape or any such closed shapes are actually good in terms of the torsion. So, as I told you that in terms of the strength, we will look into the section modulus, and I already explained the section modulus to you, and accordingly once again by with respect to a baseline design, you can get the phi b f, which will be something like 4 pi z a to the power 3 by 2, slightly different expression, but that is what we will land into corresponding to the strength. So, like we get two shape factors corresponding to the bending and torsion, and similarly corresponding to the strength, we get again two shape factors, okay, one corresponding to the failure in bending, another corresponding to the failure in torsion. For tensile load, you do not need it. Now then, whatever the material property index we have earlier discussed, like for tie it is E by rho sigma f by rho, this would not change. A tie will never be affected by the shape of it, because I told you that its basic design is such that it is just the raw cross sectional area that matters, not the distribution of it. But for a beam loaded in bending, instead of square root of E by rho, now we have E phi b E square root over rho, and for strength it is sigma f phi b f to the power 2/3 over rho. Now for the torsion, we have E phi t E square root over rho, and similarly for the torsion we have strength wise it is sigma f phi f to the power 2/3 over rho, and for column it is again very much similar, square root of E phi b E to the power rho, but for a column the strength limited design does not depend in terms of the distribution of the cross section. Now, if I look at every material, why it is so important? That is because for every material there is a maximum phi that you can get. Like for the steel, you get a maximum phi of 65 against bending, 25 against torsion, okay, and similarly 13 against the strength and 7 against the torsional strength. That same thing for aluminum alloy is not so high, it is 44, which means aluminum alloy cannot be bent, cannot be deformed to the extent steel can be bent. That is why it is less. GFRP, CFRP is also further smaller, polymer even smaller, wood is the possibly the one of the smallest, and the elastomers. So, that is happening because of the manufacturing methods, okay, and also certain competing failure mechanisms. I can tell you very approximately that if we think of an aircraft wing, for example, that aircraft wing will be having lot of struts in it supporting the wing. Now, corresponding to this case, if the bending comes into picture, and if we have three such material possible with us, the wood, CFRP let us say, and the aluminum, interestingly you would see that though the actual material property index wise wood is better, that is what we have seen in the last class, but if we consider the shape factor, wood is no good. The two competing ones will be CFRP and the aluminum. Now, for the aluminum, though you get about 40 times shape factor, but the material property index is not so high as the CFRP. So, at the end, though for the CFRP it is slightly lesser than the aluminum, because its material property is higher. So, now square root of the product of the two, CFRP becomes higher, and hence it becomes the best choice CFRP considering shape factor. Okay. So, that is how shape factor can actually change our decision. Now, I also have put the same thing here in terms of the material selection point of view for steel, titanium alloy, GFRP and wood for a stiff beam. And then there are two different property indices. One is corresponding to the square root of rho E over rho, and that will give you the masses if I calculate, and another is if I consider the shape factor with it, that is rho over square root of phi E. Now, you look at it that if you do not consider M2, M2 is with the shape factor, right. So, if I do not consider, then on the basis of this rho over square root of E, which one is going to give me the lowest mass, right. So, the lowest value of it will give, in other words, the highest value of square root over E by rho equals to the lowest value of rho over square root of E, and which one is the lowest value here? Well, we can see here that the wood is having the lowest value. So, if I do not consider the shape factor, wood becomes a good element for stiff beams, light stiff beams. But if I consider now the shape factor, then what happens? By applying all those maximum shape factors possible, we can see that the lowest is no longer 0.088. In fact, the lowest is 0.049, and that is actually 6061 titanium aluminum alloy. So, you see that the shape factor changed our decision of selection of material altogether. Interestingly, this is not only the case if I consider the overall cross section. If I consider the microstructural shape factor, that means the wood inside also will have lot of microstructures inside, then some of these decisions may actually change. Okay, I will not go into the details of it, but just keep this point in mind that all these things I have done not considering the microstructural shape factor. Now, one point then which is coming up is that the design is a coupled problem. Okay. So, we have material in one hand available with us and a particular form that we have to give in order to carry out a particular function. Remember, function is at the center. It is across the function, all these three things are there. Okay. So, keeping the function in mind, we choose a material for a particular form, but that will never give us the full story, not this one, but the you have to also consider the manufacturing part of it. Okay. Generally, in manufacturing, there are three different parts. Okay. First, the primary process. For example, am I going for casting, or am I going for a deformation based, say, forging, drawing, this type of things. Okay. Or am I going for say, for example, other type of molding process. So, this is the primary process. Okay. That is one manufacturing process that will also govern the form and everything. Then there comes the secondary process. Secondary process talks of the local shape and the surface finish. For example, drilling, milling, turning, okay, grinding, whatever you are doing, that you are doing for the secondary process. Now, some material are better from the drilling point of view, milling or turning point of view. So, when you choose the material from the secondary process keeping in mind, then also some material will get a preference in that manufacturing. And finally, there is the tertiary process in which we modify the material properties with some little shape change, like applying heat treatment and plating, etc. Here generally shape does not matter, but both of these two cases the form is governed by the manufacturing process for sure. Now, I will come to the last point of the form design, without which the discussion will not be complete. What is this last point? That is the aesthetics and industrial design. Okay. So, what is industrial design? Now, consider this is a car, an antique car which is known as MG Roadster. You all know of the MG cars. This is one of the earliest version of MG cars. Now, the design of the car is such that it is actually invite you to hop in and take it. So, that means industrial design is an applied art that creates the form of a manufactured product in a way that it becomes attractive to the customer. So, in this case, the function is not actually engineering or mechanical, but the function in this case is actually how to attract a customer. Same thing, you think of this very famous Alto T trolley 900 series. In 1937 Paris World Fair it was shown, and Alto as a very famous name, from whose name the inspiration of Alto car might have possibly been taken. Now, Alto's design of modern furnitures is something where the aesthetic plays a very important role. This is a food trolley, but designed in such a manner that it is inviting from the customer's point of view. Same thing is true for the Crystal Palace. It's an exhibition hall of 1851, great exhibition for all industrial goods, occupying 20 acres at the Hyde Park. So here also the form has been chosen keeping the aesthetics in mind. And another example I will give you, it is a famous example of typewriter. This Olivetti typewriter. It is not only functional, it is not only usable, but also it is highly attractive design. So this stand the test of time and they become classic designs. I'll just tell you, for example, the motor for a power drill. Okay, it may be that the same motor is used for manufacturing by the company, but the motor shape and composition may remain fixed. However, the designer is responsible for the housing, that is the casing around the motor, and the shape of the housing should not be only functional, but expressive, like it must express the interior mechanism and delineate the purpose and character of the drilling operation. This is something where arts is involved, and that is something where material plays a very important role. How? Well, keep in mind that every product has two basic characteristics: product physiology and product psychology. Whatever I have told you through the ASB charts, these are important from the product physiology point of view. So, selection of materials and processes which are mainly from the functional point of view, but there also exists product psychology like aesthetics of a product, associations, perceptions of a product. All of them play a very important role in terms of selection of the material. So, for example, when we talk about aesthetics of a product, we talk about color, form, line, shape, space, texture, values, all of them together, and that you can see is very apparent starting from a product which is maybe of household use like a musical system and a commercial product. For both of them, all these things play a very important role in terms of creating the aesthetic value of the product. So, that is one important point, the aesthetic value. However, I also told you that associations and perceptions of a product also play very important role. Well, what does the association means? Well, a product must give some association with respect to, let us say, the luxury of a product. Okay? So, even though the product is a pen, I will give you two examples, right. So, this is a simple pen, functionally this is the same as this pen, but you can see that while this is plastic, because cost was the only important factor while choosing this system, whereas this is metallic, and the cost was not an important factor here, because it is the perception of luxury and also the requirement of creating so many interesting, engrossing artistic features that would not be possible in a simple plastic one. So, the perception of artistry and the perception of luxury change the same pen. So, similar thing you will see in many aspects of associations and perceptions. I can give you another small example of it. Say for example, the customer wants something which needs to be softer in terms of the ergonomic nature of the system. What do we think of it? Whenever we think of softness, does it mean that the system must be having high hardness value, like we know in mechanical context the Vickers hardness or Rockwell hardness, which only talks about the surface coating, the hardness of it, or does it mean that the product should be having a large modulus of elasticity? In fact, it is the product of the two that actually governs this. So, the perception of softness is governed by square root of EH. That means it is neither E nor H, but the product and the square root of the two that governs it. So, like that we try to quantify many a times such perceptions, and then we choose the material accordingly. Now, this is where we are going to end today in this lecture. Thank you.